Hello, welcome to your flip lesson on the volume of pyramids and cones. We're going to do pyramids and cones because they behave very similar in how we find the volume of those two objects. So to start out with, let's talk about some pyramids. And I have two types of pyramids here. And these are five terms that I'd really like you to know because when I talk about these terms, I want you to know exactly which part of the pyramid I am discussing. So let's start out with the base. So in your guided notes, you might want to pause the video and make sure you fill in these definitions and know what I'm talking about. So the base is the face of the pyramid that is opposite the vertex. Now this up here, that is the vertex. So in this case, the base is down here. It's generally the non-triangular side. In this case, the base is a pentagon. And down here, the base, right below the vertex, that is a square, or maybe it's a rectangle, I can't really tell. But bases are important because they give us the name of the pyramid. So for example, this base right down here, I'll paint it. Let me not paint it green. Let me paint this base red. This base right here is a pentagon. And so we would call this pyramid a pentagonal or pentagonal, depending on where you want to put the accent, a pentagonal pyramid. And then this base here is either a square, and if it was a square, it'd be like the pyramids in Egypt, it'd be called a square pyramid, or if it's a rectangle, we would call this a rectangular pyramid. So pyramids are named based on their base. Now, the second term would be the lateral faces. And the lateral faces of a pyramid are always triangles. And they're the triangular faces that meet up at a single point. And that point is right here. It's called the vertex. Down here, these four triangular faces meet right here at this point, the vertex. And the vertex, you might as well define, is the point at which all the lateral faces meet. So here in this pentagonal prism, we have 1, 2, 3, 4. We have 5 lateral faces. Let me paint those faces green for you. Well, I'll paint one of them. So here is a lateral face. Lateral faces for pyramids, they're always the triangles that meet up at a single point. Down here we have 4 lateral faces. So pyramids have two different types of heights, and those two heights are very important to us. We have the true height, which in all formulas I notify with a capital H height. And the capital H height is the distance from the vertex directly down perpendicular to the base. In this case, there is the true height. It goes from the vertex and it drops directly down to, in most of the pyramids we work with, the very center of that base. And that is how tall the pyramid is. That's how high up that pyramid is. And so this right here, that would be the true height. Now there's a second height, and that's signified by this purple slanted line, and that's called the slant height. And the slant height represents the height of the triangular face. So if you imagine this triangle, we have a base, a little b base, and a little h height. So the slant height is not ever the same as the pyramid's true capital H height. So when we talk about how high up a pyramid is, we're talking about how tall it is perpendicular to the base. But the slant height is the slanted part. As a matter of fact, I'd encourage you right now to think for a second about which one is always going to be larger, the true height or the slant height. One of them is always larger than the other. Well, I hope you said it was the slant height, because if you drop the true height down and you connect it to the slant height, you'll notice we get a right triangle. And this slant height represents the hypotenuse, so it would be the longest part of the right triangle. So let's make sure we understand exactly what we're dealing here with pyramids. So imagine in a pyramid, and if you look at this pyramid, it has 1, 2, 3, 4, 5, 6 lateral faces. The base is a hexagon, so we call this a hexagonal pyramid. And if we flattened this pyramid out, if we just broke it down all the sides and we flattened it out, you'd see we'd have this red hexagonal base, and we'd have 6 triangular faces, all of them being congruent. Now, again, I want to make a distinction. The height of the triangle right here is the slant height of the pyramid. But when I'm finding the volume of a pyramid, and by the way, here's the formula, I want the capital H true height. I want to go from the vertex perpendicular to the base. That blue segment is the height I want. And you might notice the area of the base times the height is the area of a prism. And what we're saying is the volume, or I'm sorry, is the volume of a prism. What we're looking for is the volume of a pyramid, and that is a third of the area of the base times the height. And there's some calculus involved in how you determine where that 1/3 comes from. But in class, I'll show you an experiment where we take a prism that has the same height and the same base as the pyramid, and we fill that prism up with water, and we see, well, actually what we do is we fill the pyramid with the same base and height up with water as that prism, and we count how many pyramids it takes to fill up that prism, and it will turn out to be 3. So let's see how we do this with some numbers. All right, number 1. So if you look in your guided notes, here's a pyramid right here. And I think the very first thing you want to do is name that pyramid. So in this case, if we look at this pyramid, we look at the base, we notice both sides are equal. This is a square pyramid. And the reason we want to name the base is that's going to help us choose what formula we use down here. The volume of the pyramid is 1/3 its base times the height. And since the base is a square, then we want to say it's 1/3 little b little h times capital H. And in this case, we started out with a pretty easy one in that I think I gave you everything you need. You know little b is 14 and little h is 14. And you know the capital H height goes from the vertex perpendicular to the base. That's 24. You can plug those numbers in and do the math. And again, in your homework, and not all of you are doing this, and I'm going to send it back and have you redo it, show me the work. I want to see the formulas you're using, I want to see the numbers you're plugging in, and I want to see the answer. So show me that work. Stay organized. Let's take a look at number 2. Now in number 2, you can see from this base here that it is a square. It's a square pyramid, and if I don't say or have evidence to the contrary, you can assume the base is a regular polygon. We know the formula for the area, or I'm sorry, the volume of a pyramid is 1/3 the base times the height. And since the base is a square, we have 1/3 of little b times little h times capital H. But you'll notice in this case, I wasn't that nice. I didn't give you the capital H height. I gave you which height? Well, I gave you the slant height. So one thing you might do is you might go up to the vertex and draw in the capital H height. Now notice that this blue segment here comes from the vertex and it's perpendicular to the base. And I drew it right smack dab to the very center of that base. Now, we know that that's capital H height. Let me grab my pen. We know that that's capital H height. But how do we find out what that measurement actually is? Well, let's see here. What if we connect the very center of this base, where the height hits the base, to the slant height here? That segment right there, how long is that segment? Now remember, it goes from the center of the base directly over to the side. Well, that should be half the length of the side. So I'm going to say that that's 8. And do you see anything interesting here? I hope what you see, now watch it. This is going to be really cool. Watch it. I hope what you see is this right triangle. That was a good effect. And since we're dealing with the right triangle, I suppose that means we could use the most famous of all theorems, the Pythagorean theorem. So over here to the side, we can say 8 squared plus h squared equals 17 squared. And those of you who know your Pythagorean triples already know h is 15. So again, in our organized 3 to 4 step process, we have the formula, we plug in the numbers we want, and we get the answer. Let's take a look at another example. Number 3. Now this pyramid is a little different. This pyramid is made up of, well, it's made up of all triangles. And I would call this a triangular pyramid. So we know the volume of a pyramid is 1/3 the base times the height. Since the base is a triangle, we can substitute in 1/2 little b little h times capital H height. Now, the question becomes, how do we find little b little h for this triangle? Well, let me come over here and I'm going to draw that little triangle right there. We know each side is 10. And, well, if each side is 10, each angle's got to be 60 degrees. And when I draw in little h height, I get a 30, 60, 90 triangle. So hopefully you know your 30, 60, 90s well enough to know that little h is 5 radical 3. So this becomes 1/2 times 1/3 times the base, 10, times h, 5 radical 3, times 18, and we get one of those two answers. One of them involves a radical, the other one we used our calculator on. Let's try one more here. Let's try this hexagonal pyramid. Again, we know the area of the formula for the volume of a pyramid is 1/3 the area of the base times the height. So let's take a look at this base. This base is a hexagon. So I'm going to come over here and I'm going to sketch out that hexagon. We know 6 sides. Each side is 12. I'm going to draw in that fundamental right triangle, and hopefully you realize that this segment, this perpendicular, bisects the side, giving me 6. You know that we can get 12 of these triangles inside the hexagon, so this is 30. And I hope you've done the math to figure out what h is. So our formula here is 1/3 times 12, and that 12 comes from these 12 little fundamental right triangles that fill up the hexagon, times 1/2 BH, that part is just this little green triangle, times capital H height. Those are the numbers. Check yourself, make sure you agree with those numbers, and that's my answer. So that does it for pyramids. Let's talk very quickly now about cones, because cones really are very similar to pyramids. So we have cones, and there are basically 3 parts of a cone that we're concerned with. This point right up here is known as the vertex. If I go from that point directly down to the center of the cone, I get the height of the cone. And of course, we have this slanted height, which you know we call the slant height, and that's a cursive L for slant height. But the volume of a cone is the exact same formula as the volume of a pyramid. So the formula for the volume of a cone is 1/3 times the area of the base times the height. The only real difference is, what shape is the base of every cone? Well, the shape of every cone's base is a circle. So we can adjust this formula slightly and say that the volume of a cone is 1/3 pi r squared, the area of the base, times its height. Now, I didn't give you any examples of cones because it's a very straightforward basic formula, and I'm going to let you play with that in your homework. So in tonight's homework, please, 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 if you don't want it sent back to you, make sure that you show me the 3 parts: the formula, the numbers you're putting in, and the answer. So good luck with your homework tonight.